In this video, we will be learning this theorem, countable additivity of integration. You can see this, is that the theorem? Yes, theorem. You can see this theorem in the fourth unit of measure and integration. This is the first theorem that you can see in this section, section 4.5, no? So, this is unexpected, I think. So, let's learn it, okay? Here you can see the statement, and I have the statement in my notes. So let us learn using that notes. So let f be integrable over e. You are taking a function f and you are saying this function f is integrable over the measurable set e, okay? And n equal to 1 to infinitive. That is, you are taking a collection of measurable subsets. E is the measurable set. Subset of this measurable sets are E1, E2, E3, etc. E infinitive. So they are talking about that now. En equal to 1 to infinitive be the disjoint collection of measurable subsets of E whose union is, when you find the union of these E1, E2, E3, E4, E4, etc. E infinitive, when you find its union, you are going to get E. Okay, so that is how you are, if these two are there, then this condition will be satisfied. This is what? This is our countable additivity of integration theorem. Can you understand this statement? Imagine a function f and you are saying that function f is what? Integrable over e. You have to know what is e. E is the measurable set. Okay, now you are having disjoint collection of measurable subsets of E, that is this. Its union is what? Our measurable set E. Then you have to prove this equal to this. Okay, so let's start the proof of this theorem. Let n be a natural number. You are choosing a natural number, that is n, and let fn equal to, you are taking like this. You should not forget this, okay? If you are not able to recall this at the time of writing the exam, you could not proceed. Okay, so keep this in your mind, recall it again and again when you learn it. Let fn equal to union I equal to 1 to n ei. Okay, fn here ei, don't get confused. Define, you are also defining this fn, small fn equal to f into chi capital Fn. You are defining these two things. Then mod fn is equal to this modulus of this fn equal to modulus of this. No, you are taking modulus to this so that you are getting this. This value will be less than or equal to mod f. Okay, this value will be what? Less than or equal to mod f. There might be some of the conditions you may have in the beginning of the, sorry, in the what you can say, before this theorem you may have this result. Okay, if modulus of f into chi fn will be less than or equal to the value of this, where you know that f is integrable, no? The statement you are having, you are writing that. Also fn converges to f on e. Also given that e is equal to this. This is also given. Union of disjoint collection of measurable subsets is equal to E, no? You are having that in the statement, so you are writing that also. You are writing fn converges to f. How you are saying that? I think you are saying that from here. Let me see in my notes. Oh, in my notes also there is nothing, no details about that. So here I think mod fn less than or equal to mod f, no? Maybe from this result they are saying fn converges to f on e. Okay. Okay, what are you doing first? First you are taking a natural number, that is n, and you are taking fn equal to like this, union I equal to 1 to n ei, and you are defining fn equal to f into chi fn, and then you are taking modulus to both the sides. So that you are writing this value will be less than or equal to mod f. You know that in the statement you are having f is integrable, so that is why you are writing where f is integrable. And what you are doing is also from this you are saying fn converges to f. Also you are having this also. You are writing all these things from the result you are having already. Okay, you have to keep all these things in your mind. Now from Lebesgue dominated convergence theorem, you are having this theorem. Say very important theorem. Just in the previous the video, I shooted a video by explaining this theorem also. You can see that video in the playlist of measure and integration. Okay, go to the home page of my channel and there you can find a playlist. There if you click, you can see measure and integration. Within that you can find so many videos. There you can find this theorem. From Lebesgue dominated convergence theorem, you will get this result. You are writing that. Now write limit tends to infinitive as it is, integral e, right, like that, and fn in the place of fn you are substituting this value. Already you have took like that, no, you are just substituting that. So here you are getting this. Now limit tends to infinitive, integral fn f, that is you are writing from this to this, you are writing using a corollary. Okay, how you are writing? You are writing integral and write the value present here, present suffix to chi, so that is fn and then this value. You can write like that using a corollary. And then limit n tends to infinitive, integral this f. The place of fn you are putting e1, e2, etc. up to union of these values. How? You have to like that, no? Fn equal to this, you have chosen like that. So you are using that here. So that in the place of fn you are writing this, and then limit n tends to infinitive, you are splitting the integrals for e1, e2, e3. You are having this, no? So you are splitting integral f e over e1 plus integral f over e2 plus etc. plus integral f over en. Is that clear? Now after that what you are doing is write limit n tends to as it is. Here it is in plus, no? Then so you can put summation. From 1 to n you are having, so I equal to 1 to n, and in the integral ei, because I varies from 1 to n, no? So that is why you are writing like this. This can be written like this, and from this you can write limit n tends to infinitive, no? So here in the next step, in the place of n you will put infinitive and write the remaining as it is in the previous step. So this is what you have to prove in this theorem. So you have proved it, hence the proof.